That only took 7 minutes, so we'll have to see how that goes. All right, so welcome. We're going to start in chapter 6. What I will be doing is backing up every once in a while to go through some of the earlier material. You should have seen the syllabus. It looks like most people did pretty well on organic on the exam 1. I know that y'all got a couple of attempts, it looks like, to take that. So, you know, we'll work through that. On the syllabus, you know, we're using the same book. I like Klein, it's a good book. It's expensive, but it's a good, solid book. Actually, it's probably one of the best ones out there. I like to use Sapling online homework now because it wasn't in your original section. I'm not going to make it required, but I do think it's one of those things for people that like to practice a lot. It's $40, so it's helpful. It's kind of like getting a tutor. You do a lot of practice problems. I'll set up the problems. I'm waiting for the company to actually engage that. But again, it is totally optional. I don't feel like it's responsible to force everybody to spend more money. But if you were paying for tutoring, or if you think it's useful, you can do that. I'll also be posting some additional practice problems, what I used to call action center problems. They will have keys. Those will be up. And then, of course, we've got problems out of the textbook. So today, let's start in chapter 6. And we'll get going. I'm going to leave up the chat. So if anybody has any questions, please put it over there. If you see a chat and I don't notice it, feel free to interrupt me, because it's hard to be thinking about high-level organic chemistry and following a chat at the same time. So please just jump in there and say, hey, Dr. Morvant, somebody's got a question. Okay, so in chapter 6, yes, sir.
Speaking of questions, I have a question.
Yes, ma'am.
Is the best way to go about your lectures is just to, if you have any like notes that we can print out, or is it going to be styled exactly like what we're doing right now?
It's going to be like we're doing now. I believe the best learning theory that it's good to be dynamic, especially with dynamic material. And so organic is a very dynamic structure. So PowerPoints are very static. And so I tend not to use PowerPoints, which usually means that I'm doing everything in real time. And so there's no notes to print out before. After I'm done with class, if you miss something, right, or if you want to check it, I'll put what I'm drawing right now online, as well as the recording. And we are recording. Okay. And so those will both be up. I usually post my recordings on YouTube rather than through my media, but that's just my preference to make them available to anybody that wants to get them easily. Okay. So there's no pre notes. What you can do is read ahead. So wherever we end today, just go ahead and read ahead. That'll give you a little idea of what's going on. Okay. So chapter 6, we're going to start with looking at energy mechanisms, dynamics, structures, looking at enthalpy, entropy, delta G, kinetics, and then we'll get into some base ideas of mechanisms. So one of the important parts of organic chemistry is understanding how things happen so that you can predict what's going to happen. And that's a lot of what organic is about. And so this is the section where we get into some of that detail so that you can start to move forward on that. So let's start by looking at enthalpy. And the nice thing about some of this is that, well, it's a review of general chemistry. So enthalpy, you might remember, is delta H, okay, and usually given it as Q at constant pressure. Okay, and Q is heat. So we're looking at here is the change in heat at a constant pressure. So if we think about reactions, almost always they are going to be at constant pressure. Now the temperature may change, right? But for delta H, we're thinking about a constant temperature, and the standard pressure is 1 atmosphere, right? So that's 760 bar. That's where we are right now, right? So, okay. When we look at our reactions, we have two main types of processes that are going to occur in reactions. First one is homolytic. In homolytic, we separate a molecule, and each of those shared electrons in that bond is going to be going to one side or the other, right? So if we look at the bonds, we're breaking those apart, and you can see that we're getting two radicals. Okay. So the bond is breaking evenly, homolytic. Turns out that there's not a lot of homolytic reactions we're going to be looking at. There's a whole chapter on radicals, but most of the reactions we're going to be looking at and that you've looked at so far are going to be heterolytic. In a heterolytic reaction, both of the electrons will go to one side or the other, usually the more electronegative atom. And so if we look at that, that means we're going to end up with one that has an electron deficiency and that one that has an electron rich. So we have electron rich and electron poor. And so as we look at these, right, we have heterolytic and homolytic. Now, to figure out what's going on with enthalpy, right, we want to look at bonds broken, right, minus bonds formed. And it turns out that the homolytic is the way we can kind of guesstimate this. So predicting the energy of enthalpy is not overly difficult, but it turns out that the best data out there is actually homolytic. So often when you're using a homolytic process to give us an idea about a heterolytic reaction. And so the best way to look at these is to calculate these is to actually look at bond dissociation energies. The bond dissociation energy is delta H naught. The naught stands for standard pressure, right? That we know is 1 atmosphere, and standard state. So standard state is if hydrogen is a gas, then the standard state would be hydrogen as a gas. Okay. Questions about that? So let's pull up the data we need. This is in your textbook. Okay, and we have a big table of bond dissociation energies, right? And if we look at the bond dissociation energies, you can see that we have different types of carbon compounds, right? So we have a primary, right? We have a secondary, and we have a tertiary group. And because of the electronics of that carbon, because of the different hyperconjugation back to that carbon, the hyperconjugation is donation of electrons back to that carbon. So we can see the primary halide versus the secondary halide versus the tertiary halide. We have different energy dissociations for that. So we would want to look at that. Similarly, when we look at H, the hydrogens over here, notice that we have a lot of different carbons, right? We have one where it would be an sp2 CH bond, but we also have one that's allylic. So when we're using this table to do some homework and some calculations, it's important to be specific, right? So we have the methyl here. Right, and then primary, secondary, tertiary. So how would we use this table? Well, let's go ahead and do a problem together. Okay. So let's say that we had, and as we move on, we'll get more comfortable with showing things in its condensed form. But for today, I'll go ahead and break this one out. So if we take this radical reaction here, we're going to take ethane and react it with chlorine in light. So when we're looking at this, we want to look at the bonds broken, right? And the bonds formed. That's going to give us, okay, and we don't have to look at everything. We just need to look at the ones that are actually being broken, and because all the rest are going to be the same. So if we're going to subtract the CH bonds that's being broken and then formed, just a lot of extra work. So if we look at what's actually being broken and formed, right, we can see that this bond is no longer there when we go to the other side, right? So you can see
Real
this
quick,
bond is breaking. Yes.
what is written underneath the arrow?
H nu.
H.
So it's Planck's constant and light. That's light energy.
Okay, okay, thank you.
Yeah, so instead of heat, so you have reactions that are thermal and you have reactions that are processed with, instead of heat energy, light energy. So H nu is the energy of light. And so that's just, so it's a funky looking H and a funky looking V. So does that help? It's Planck's constant and frequency. All right, so when we look at this, right, we've got, if we look at the bonds that are changing, this bond's changing and that bond's changing, right? And then this bond here is changing and that bond's changing. So if we highlight all those in red, so here we're going to have a bond, here, here. So we got 4 bonds. Over here on the making side, we've got the CH bond, and we know this is a secondary, right? And then we've got our Cl bond that's being broken. Over here we have a Cl bond that's being formed, and again that's secondary. And here we have an HCl bond being formed. Okay, so from that information, and I get this from just the observation, then I can go up to my chart, okay, and I'm looking at not, I'm looking at, sorry, that's not, excuse me, this is primary. Primary, right, primary, it's only got 1 carbon attached. So if I go up here and look at this one, I'm going to see that here is the bond energy I want, 410. We most often use the kilojoules per mole. There are a couple of calculations that use kilocalories per mole in the text, so that's why this is here, but kilojoules per mole is our standard. So therefore we got 410, so we can write this down, kilojoules per mole. Yes.
Someone asked, how do you determine whether it's primary or secondary? And that's just by the number of carbons that are
carbons attached. Yeah, let's look at that real quick. So if we have a carbon that's attached to some halide and it's got nothing attached to it, we refer to that as a methyl, right? Then when we look at something like this, right? I'm looking at this carbon where the halide is attached. Right, this is going to be primary because there's 1 carbon attached. If I then look, right, this is going to be secondary. And then right? This one has 3 attached. So this is tertiary. And now carbons can't have 4, but if we did have 4, let's say not for carbons, but for nitrogens, right? This could be known as a quaternary. And again, it's based on how many carbons are attached, okay?
So I have a quick question. This is kind of sound dumb, but are we only focusing on primary, secondary, and tertiary in this unit? Like, I mean, in this like OChem 1 class, or are there more?
No, if you think about carbons, there's really only 4 choices. You got when you're thinking about alkyl halides, alcohols, amines, and you're looking at the carbon, there's really only 4 choices. So it's not like we're focusing only on methyl primary, secondary, and tertiary. It's that is the only choices that we have. So when we look at, you know, these groups, this, and this, each one of these behaves slightly differently because of what's going on. There's an electronic difference because the carbons can, the hyperconjugation, which we'll get to more when we get to reactions with carbocations, right? So we've got an electronic effect, but we also have a steric effect, which we're going to get to when we get to kinetics in a few minutes, well, or tomorrow. Kinetic effect, because if we think about this one, the carbon has less big bulky groups around it, and as we change, we see more. So the reason that we use primary, secondary, and tertiary is help us to understand the different reactivities of these. Each of these is going to have a different priority when we start to look at our reactions. Does that help?
Yes, thank you.
Okay. It's not that we're only forming this, it's that those are the ones that are possible. And there's, by knowing if something is tertiary, it gives you a shortcut to know its electronics and its sterics. By knowing something is a methyl, it gives you a shortcut of its electronics and its sterics, right? It's less electronically stable, but is also less sterically hindered. When you look at a tertiary, right, it's more electronically stable, but it is more sterically hindered, right? So by identifying that, I can decipher which direction the reaction is going to go. So it's a, we don't like the stereotype, but if you see a truck, you know a truck. If you see a tertiary, you have an idea of what the tertiary carbon is likely to do. Just like you would see a truck, you'd imagine it to be able to haul lumber, where if you saw a Camry, I probably wouldn't haul lumber in my Camry, right? And so there's different functions based on different structural sites. The quaternary, there is a carbon that's quaternary, but it's not alcohol, a amine, halide, right? So you can have a carbon that has 4 things attached to it, and that carbon is quaternary, right? But what do we see when we look at this? Well, is there anything other than carbon attached? No. And what we're going to learn is that carbon-carbon bonds are incredibly strong. Carbon-hydrogen bonds, not that strong, but they usually, for heterolytic reactions, need something. So the only reaction this could go through would be a radical abstraction, but it's not going to happen at this carbon. It's going to happen at this carbon, right? So quaternary carbons, things that are attached by 4 carbons, that carbon, because of the strength of the carbon-carbon bonds, becomes non-reactive. So if we think about organic, it's not that we don't have quaternary carbons, but quaternary carbons don't do much, right? Best thing you can do for a quaternary carbon is to react at the carbon that's next to it, and that's the process, right? So that's why we focus on the methyl to tertiary. All right, so let's go back and get some of our data points here. So we look at chlorine-chlorine, so we go back to chart, we find our chlorine-chlorine bond here, right? So we just look at it, that's 243, so we'll write that down. right? We see a carbon with a chlorine. So again, we're looking at our primaries. That's here, 339. And then our final one's got the hydrogen on it. So we can see hydrogen, hydrogen. Here it goes, hydrogen, chlorine, 431. And whenever we bond breaking takes energy, right? So that's going to be 410 kilojoules per mole plus 243 kilojoules per mole, right? That's my bond breaking minus then the 339 kilojoules per mole. This is the bond forming plus 41 kilojoules per mole. And then as you would do in Gen Chem, right, you're just going to plug and chug. And so if we do that, then the delta H naught for this is going to be negative 117 kilojoules per mole. When we look at the delta H, right, if we go down, and again, a little bit of, if we're going down in a negative direction, right, then that is going to be in exothermic. If we go up in energy, right, so that's delta H naught equals positive, right, then that's going to be endothermic. And hopefully these terms are somewhat familiar. So in this case, this reaction is going to be exothermic. Now that's the first step to figuring out whether this reaction would be spontaneous.
Excuse me, Professor.
Mm-hmm. Yes, ma'am.
If we get one of these kinds of questions on an exam, will you give us that chart?
I'll either give you the chart or you'll be given the data you need. So maybe a subsection of that chart.
Perfect. Okay, thank
Okay.
you.
You're not expected to know this chart. This is things. There's actually a huge book of these that we would go look up if we were going to do it in the lab.
Okay, thank you.
Okay. Yeah. No, you'll either get this chart or you'll just be given a 5 or 6 numbers and be able to calculate this. It's really straightforward. You might have seen something similar in general chemistry. It's not difficult, and there's some practice on it. You know, I'll post some practice problems, and there's some practice problems in the book. Okay, so that's heat. Okay, let's move on into enthalpy. Let me check my time. Okay, for enthalpy, right, this is going to be our delta S.
Did you mean entropy, Dr. Morgan?
Oh, yes, I did. Thank you. I'm all proposal today.
No worries, so are we.
Yeah, it's okay. We're good. Okay, so entropy is delta S. It's spontaneity, if you want to think about it, or chaos. So if we think about the second law of thermodynamics, right, it says that entropy total is always increasing. And so if we think about that, then what we're going to see is that within the system, so it doesn't mean that entropy always has to increase, but that the total is, which means you can be looking at a reaction, right, a system and the surroundings. And so if we decrease entropy within a system, then we're increasing the entropy within the surroundings. Okay. So if we increase entropy, that means that that's going to be a spontaneous process. There are delta S calculations in organic chemistry. You use them a lot less. So we look at more conceptual ideas of the entropy. And the thing is to think about, is the chaos in this system increasing or decreasing? So if I looked at A plus B going to A and, I'm sorry, if I look at AB going to A plus B, is that an increase in entropy or a decrease in entropy? Well, I'm going from one
Breaking a
molecule,
bond?
right? Well, breaking a bond would be enthalpy. So think about entropy, not breaking the bond, but, well, we are breaking the bond, but not about the bond, but what's happening in space. If we think about
increase,
a container,
right?
It would increase. So if we think about here, all I have is a homogeneous mixture of this molecule AB, right? But over here, what I have now is a heterogeneous mixture of A and B, right? And so this is going to be an increase in entropy from a homogeneous mixture to a heterogeneous mixture, right? So I've increased my entropy. Similarly, if I think about a molecule like this, and I take that and I turn it into a molecule like this one, right? Am I increasing or decreasing the entropy?
Increasing.
Increasing. If we think about this structure, right, and this goes to your conformations, right, I really only have two choices, right? I have that and it can move, but it's really only moving between the two chair conformations because it's a 6-member ring. But over here, if we think about it, every single one of the bonds can rotate, right? So now I have rotation here in 360 degrees, here in 360 degrees, there in 360 degrees, right? So I've got a molecule now that has a lot of different options, not just the transformation between two chairs. And so I've increased the entropy by the freedoms of rotation, right? And you'll hear people say that, you'll hear me say that. So freedom of rotation. So this is an increase in entropy. So conceptually, what the book asks and what I'll ask is really to be thinking about entropy from a conceptual standpoint versus a calculation standpoint. For enthalpy, it is important to be thinking about what's happening with the numbers, because the number is going to help. But with entropy, it's easier to think about what is potentially going on by thinking about just, is there greater or less? So if we look at these two examples, with the reaction of hydrogen going to adding across that double bond, which we'll see when we get to that chapter. Well, here I'm going from two molecules, right, to one molecule. So it's the opposite of what we saw up here. So this would be a decrease, right? This would be a decrease in entropy. I'm going from a heterogeneous mixture to a homogeneous mixture. And so therefore I'm decreasing the entropy of the process. Now, changes in enthalpy and changes in entropy by themselves are not going to decide whether a reaction will occur. They're both part of the process. So this reaction is one that occurs, but it seems to go opposite of the entropy. Now, if we think about the second law of thermodynamics, what does that mean? Well, if entropy is decreasing here, what has to happen outside the system? Well, it has to increase, right? So if we think about this, we can decrease the entropy within a system. It's just outside that system, it's got to be increasing. What I usually think about this is, you break a bowl and then you try and put the bowl together. Well, you really have increased entropy because now you have a crack in the bowl and you've got the glue and you got the empty glue container and you got glue on your fingers and things just get really bad. Or if you spill milk, right, then you're going to use a rag to get the milk and now you've created more stuff. You can go backwards, but you're actually somewhere else. You're creating more entropy. So that's the way to think about this. In this last one, right, we're going from degrees of freedom to less degrees of freedom, right? Because now we have a cyclic. So this is also a decrease in entropy. Okay. So for delta H, we can use our bond dissociation energies to give us a good idea whether something is going to be favorable, meaning negative. In entropy, we always want entropy to be increasing. So therefore entropy, right, a positive entropy, right, is a spontaneous reaction or spontaneous process, right? Where delta S negative is non-spontaneous. Okay. And that brings us to how do we put these together to really see if a reaction goes, and that's Gibbs free energy. And again, should have touched on this a little bit last year. Okay, and this is delta G. So delta G is going to take our enthalpy minus then T delta S. Okay, and so T is going to be temperature. And we can think about that the entropy changes as temperature increases and decreases, right? Because the molecules are going to be moving at different speeds as they go higher temperatures, going to be moving faster. That's an increase in temperature. Cool it down, we get less change in temperature, less entropy. So delta G, when delta G is negative, that's a spontaneous process. When delta G is positive, that's going to be non-spontaneous. If we look at our diagrams, again, here, if we look at delta G versus delta H, this is negative, this is going to be exergonic. And then if it goes up, now note that we're talking about spontaneity and exergonic and non-spontaneity and endergonic. It doesn't mean that a positive delta G will not allow the reaction to occur, but if that reaction is to occur, you're really going to have to force it. Now, you might force it by removing a side product so that the reverse reaction is not plausible, or you're going to change the conditions to where it becomes delta G. So if we think about delta H, we've been talking about standard pressure. So we could take a endergonic reaction and turn it into exergonic reaction by not using standard pressures, but by using high pressures. That then could change a reaction from endergonic to exergonic. We can also make something endergonic by to move forward by just removing a product that would allow it to go in reverse, because most reactions are reversible. Okay. All right. Questions about these? And again, these can be calculated. We're not going to do it in organic chemistry, you'll see it in PChem. If you're if you're a chemist, you'll see it again in PChem, and you'll do lots of calculations on delta G. Here, if you look at these two firms, if it is favorable if it's exothermic, right, and we see a negative entropy, a positive entropy, then that reaction is always going to occur. So if we look at some examples, delta H is negative and T minus S is positive. Oops, that's negative, right? Then this reaction is going to occur. Because delta G is going to be negative. If we see delta G with H negative and T delta S is negative, right? Then when will delta G be negative? Okay.
When the
Delta
enthalpy
G.
is greater than the entropy?
When the enthalpy is greater than the entropy, and that'll be the case when delta T is small, right? So low temperatures, right? So we need the entropy term to be smaller than the enthalpy term, and we can do that, right, by low temperature or really small changes in delta S. If we look at delta G, where delta H is positive and T delta S is positive, here then delta G is going to be negative at high temperatures, right, or low delta H, right? So enthalpy, if the change in enthalpy is very small, or conversely, if we can make the entropy term very positive, very high, so we can go to high temperature. And then the last one is when we have both of those against us. Right. And then in this case, right, then delta G is going to be positive, right? So it's not, there's no, in this process, there's no way to really make this spontaneous. Doesn't mean the reaction couldn't potentially occur, but it does mean that under the standard conditions, you're probably not going to get this reaction to occur without it reversing very rapidly. Okay, so if you know your delta H and your delta S, it can give you a good idea of whether that reaction is going to be spontaneous or not. Okay, looks like we have just enough time to cover one more topic. And this one's a big one, equilibrium, right? So A plus B goes to C plus D. And we see this a lot. Most reactions are reversible. Okay, so we get a negative delta G. But if this is reversible, how do we figure out where the equilibrium lies? And it turns out that the equilibrium, KEQ, is the products, concentration of the products, concentration given by the brackets, over reactants. And in this term, right, is going to be CD over a concentration of A and the concentration of B. And then that's related to delta G by negative RT. R is constant temperature, and then the natural log of KEQ. Okay, so if we know the equilibrium, we can figure out what the delta G is, and then we can change the process by looking at those. Let's see, to help you see this.
R is negative 8.31 joules per mole.
That's correct. I don't believe the book has any calculations on these. It is something you'll see more when you get to biochem and of course PChem. PChem is all about numbers. This one's more, again, kind of conceptual. Do you understand what it means? And this chart really helps this quite a bit. So if we look at delta G differences, so if we look at our standard delta G differences of 0, right, that means our equilibrium is 50-50. But once we get to delta G's of even 17 kilojoules per mole, you can see that we're really getting to a high equilibrium rate. In fact, we're getting to an equilibrium of 99.1 that we'd say that reaction, right, is quantitative, meaning it's going to occur. We wouldn't expect to see much, right, 0.1% of the back reaction. So sometimes in Gen Chem, what you would have seen here is that they would just say this reaction goes without equilibrium, right? Because so much of it goes that you're not really worried about it. In organic, we start to get to the nuance of this is still an equilibrium, but it's really heavily sided on one or the other. And we can see here, once we're about 11, right? We're 99, you know, -6. So it doesn't take long with these to get to the point where this reaction is really going forward versus back. Reversely, right, if we look at reactions that are positive, so endergonic, then all of a sudden we can see that the forward reaction is not really occurring. So if we want this reaction to occur, we've got to be doing something to get this reaction to occur. And you're going to see a few of these as we move forward. And what we can think of is isolating that product. So there are equilibrium processes where if I can isolate the product, the equilibrium keeps going forward, right? So it's kind of like a cycle. I take off 0.1%, I take off 1 point, and what that does is that keeps bringing down, and you can actually do it. But what you're doing is you're driving the reaction forward by removing the equilibrium product, right? So that this formula up here, I'm removing D, so it's always getting removed, so the reaction is going forward, right? So some tricks that can occur with these, and you'll see a couple of these go as we go forward, okay?
What would be a typical exam question that you would use for this? Would you just ask us like the percentage of products at equilibrium given a specific like K equilibrium value?
Only if I gave you the chart. Again, remember, we're going to be looking at this somewhat conceptually. The practice problems are going to help. Okay, so when you see the practice problems, you're going to, but the way I look at this is really you need to be getting your mind around the conceptual idea of how the delta G relates to the concentration of your products and reactants, right? And how that products and reactants relates back to delta G. Okay. Does that help? So when you see some of the practice problems, it's going to help you determine this. You may be given some concentrations and then had to do minus RT ln equilibrium. I tend not to put that on exams, but it might be in some of the practice problems. What I would want you to see here is, and again, if I, like before, I'm not going to ask you to give specifically these numbers unless I give you this chart.